All right. So where we were last time is we were, to continue, we were talking about the criteria. We were talking about the notion of being a set, a particular restricted sort of a type, and I was giving a particular criterion. I just wanted to finish that off, which is showing that something called Hedberg's theorem. So recall we had the idea, we defined a type as a set, okay, if and only if. We said that if you take any, or you can say is by definition the type, however you like to say that, for any x, y, and a, and for any proofs that x is equal to y, those proofs are themselves equal. There's at most up to, higher equational reasoning, there's at most one path between any 2 points in that set. Shortly, in a minute, we're going to define this to mean, we'll have another notation, is we'll say that the equality in A is a prop. That's what's going to happen in a minute, okay? Which you'll recall, I think we talked about, we might have talked about, we did talk about what is prop, because we defined is prop. I'm not sure if I did or not last time, but let me write it down. So this is defined in the following way, if and only by definition. It says any 2 elements of that set, or that type, are equal. Okay, so we say pi. Okay, so any 2 elements of that type are equal. So I think we discussed this. Yes, we did. So we discussed this, which is the idea that it is. You could describe this as being a sub-singleton. Okay, and which is the idea that there's at most one proof of any. Most one element of the type A, because any 2 of them are equal, at least up to higher homotopy. And this is described, the convention is a prop, and we talked for a little while about the nature of being as a prop, the nature of the terminology. There's a possible terminology conflict there, but anyway, there's a technical notion called is a prop, which stands for that, and whether we like the word or not is not really that important. Okay, so we want to just sort of say that those are the 2 definitions. So we talked about that last time. And then I put something on the piazza I mentioned is that that the negation of any type is a prop. That we always have is prop not A, okay, for any type A. I, in fact, was interested in it in the case of double negation, but then I realized afterward, of course, that and the reason is, right, why are any, remember where not A is by definition A arrow 0, right? And so why would that be? Well, it's completely clear. If you have X and Y in not A, all right, is that what I want to say? Then I want to show that that x is equal to y in not A, and we're in a situation where we have function extensionality. So it suffices to show that for every u in A, xu is equal to in 0 to yu. Okay, because that's just function extensionality, because that's a function type, and of course, if we have the assumption that x and y are in not A, and we have xy is equal to not, if we have a u in A, then obviously the evidence for the equation is going to be you abort our assumption. Let us take x applied to u, I don't know, whichever one you like, is going to have this type, and therefore it will be true. Okay, because we have a contradiction. And so the particular case we were discussing at some length last time was a situation where I wanted to deal with the double negation as a kind of squashing operation. And, and from that point of view, the purpose of the double negation, one negation enough is to turn it into a prop, but we also wanted to retain as much as possible the same meaning. And so the double negation says we can take a type and squish it so that it has at most one element, and turn it into a prop, and then we talked about the double negation translation and all that thing. Okay, so that was a sort of thing we were talking about last time, so that's a brief recap. Okay, so really what this is saying is the equality if the equality for a type is a proposition or is propositional in this technical sense of the word propositional, then we say that it's a set. Okay, so it kind of has some, so that it maybe, I guess it should have some feeling or some intuition for you that being a set, it has this quality of being discrete. I mean, any two elements, any two proofs of equality, there's at most one between them. So you might have none, they're just not related to one another, or if you have two proofs of the same equation, then those are in fact the same. The path structure is degenerate. Okay, so for if I pick any two elements, x and y, maybe there's no path between them, or there's a unique path between them, unique up to higher homotopy. So there could be, in some sense, you could write down several different paths, all of which in the higher dimension turn out to be equal to, to each other, so that you can collapse them down and there's one. So that's the sort of picture you're supposed to have. And then if you think of those as just being identified, all right, just because if the path is representing a proof that they're equal, all right, so this is a proof that x is equal to y. So then what you're saying is, just drawing a picture here, is the set is homotopically discrete, that you have this kind of structure, okay, that there's no non-trivial relationships amongst them like that. Okay, so that's the idea. Yeah.
In the last step of your proof, you're just using like the nullary version of coproduct equality or something?
The nullary version of coproduct equality. I didn't need to know what the definition of path in zero is. All I needed to know is, by function extensionality, it suffices to consider an arbitrary u and a under the assumption that x and y are in not a. And therefore, well, pick whichever one you like, x or y. This is in zero. And so abort of that is in the desired equation as an element. I'm aborting into the desired equation. And so, you see what I mean?
Yeah, you're using the abort at that time.
Yeah, this is, this is at x, y equals 0, y, xu equals yu, sorry. In here, right? That's what I'm putting in here, and then I'm just I couldn't care, in a sense, couldn't care less at this point what type that is, because I can abort into it. Okay, yeah. Okay, so that's the idea. So last time I stated it as prove not on A is a proposition, which is true, but if you look at if you try to do that argument directly, you'd realize that what you're doing is showing that negated propositions. So that's why, for example. That's why, for example, there's a famous thing of Brouwer's writings from the 30s, which puzzled people, I think, at the time. That's the impression I get, is that since negated propositions have no computational content, that is, I'm tripping over my words now because I use proposition synonymously with type, and then there's the technical meaning of prop here, so I can't, that's one of these terminological clashes. Okay, since negated things have no computational content, then you get that not such things imply such things. Okay, so the three nots can be canceled into one. And I get the impression that a certain number of people found, because there's only one thing you could possibly put here. Okay, that's the what's going on. Once you've squished all the computational content out of something, then you can get things like stability in this form. And And that was like, I think that was one of the things that, I don't know which would have been more bizarre given that he was working in the 1930s. The fact that this is true, or had it turned out to be that it wasn't. And there was like, you could stack up as many, that would be really terrible. But that didn't happen, but this is true. But it's I think it looked pretty peculiar, all right, at the time. That's the impression I get. To be like noodling about, well, 3 are the same as 1, but 2 is not the same as none. And so, but that's the way it went. Okay, so it makes perfect sense, of course, because all those ideas of Brouwer's made perfect sense. It's just that it was hard to adjust people's minds to it, I think. Okay, so then the next thing is that I just wanted to finish up is we had a convenient criterion, okay, for being a set, which says that if basically a type with decidable equality is a set, okay. Okay, so remember that what does decidable equality mean? That says, by definition, that says for every x and y in A, either x is equal to y or it's not. Okay, well, and then if you want to write that in type notation, plus this arrow 0, whatever, however you'd like to write it. Okay, so either 2 elements are equal or they're not. Okay, so this in a certain way expresses the feeling that I was trying to convey last time, which is the terminology of isprop that's being used here for subsingletons is, to my mind, a vestige of classical reasoning. But it's not all the way to classical reasoning, because it's very tempting to say this is expressing either 2 elements are equal or they're not. But no, that's not what it's saying. It's just saying there's at most one proof most one proof of equality between any 2 elements. And if you're used to kind of classical reasoning, you would say, well, in other words, either they're equal or they're not, and equal in a unique way or they're not, but that's not what it's saying. Okay, so the idea is that so from that point of view you can kind of feel it. If I have the even stronger criterion, that would be the way I would think about it from a constructive point of view, the even stronger criterion that equality is decidable, then it will turn out to be that the type is a subsingleton. Okay, so that's the idea. Okay, so the proof that I have in mind goes in 2 parts. It says, well, I'll write it in, I'll specialize it to this context. I'll say decidable equality implies stable equality. And stable equality, by definition, means for every x and y in A, if 2 things can't fail to be equal, then they are equal. And so again, you recognize that, from a classical mindset, that's a tautology, but from a constructive mindset, it's not the case. If their equality is irrefutable, their disequality is irrefutable, that's what I should have said. If their disequality is irrefutable, that's not the same, their disequality is refutable, okay? Did I say it right? Then they're equal. Okay, that's the statement of that. So it's tautologous from the classical point of view. Well, in fact, in general, right? So I'll just put in here. In general, what we have is that if you have law of, in fact, you can write it in a very special form. You can prove that if you have, A or not A, then not A implies A. So we can. That's a particular. That's a general fact. Doesn't matter what A is, and so this remark is just an instance of that. Okay. So why is it the case that A or not A implies not A? Well, let's do it quickly. I do a case analysis on A or not A, right? with the intention of deriving A. So if A holds, then A holds, and I'm done. If not A holds, then I apply this assumption and abort it, and then I'm done. Okay? And so that's so the thing I want to point out is you can put at the outside here the for all A. Okay? In other words, any particular instance of the law of the excluded middle implies that same instance of the double negation law of the double negation elimination. Okay. In other words, rather than saying the law holding in general implies the law holding in general, I in fact just say for any particular choice, it works like that. So that's just a logical fact, okay, that you can write down. And then the other thing is that then what we're really going to prove is stable equality. Okay, implies sethood. All right, write it like that. So since this is so trivial, you could have just as well as said Hedberg's theorem is stable equality. Every type with stable equality is a set. It's just that somehow decidable equality feels more like usable or something. I don't know what. It's for some reason. Okay, it just seems like a nicer way to state the theorem. Okay, so that's the idea. So we'll show that stable equality implies sethood. Okay, so here's what we want to do. So what we do is we suppose. So the proof of this thing is we suppose we have a witness. Okay, X, Y, and A to the stability of the equality for that type. So this implies that. Okay, so that's the idea. So that is assume equality is stable. Okay, so this states that equality in A is stable. Okay, that's what we're doing here. So the assumption says that. Okay, so what do we have to do? Right, so what we want to do is we want to show that A is a set, which is defined up here in the upper left. Okay, so how do we do that? Okay, so we're going to show a simpler. The argument is going to show as follows. It's going to say that any self loop, okay, is reflexivity, and that's enough to give us something as a set. So I can say suffices to show, right, for any x in A, and P is a loop in A. So if we have a point and we have a loop, that loop, that this implies that basically that P is equal to refl A of X in the appropriate type. Okay, X equals X in A. So this would be X equals A, X here. Start to run out of space. Okay, so that's the definition. Okay, so the reason is because for X equals Y, you can just look at X times Y inverse and show that that's refl. Okay, and then you'll say that X is equal to Y. Okay, so it's enough to show that every self loop is reflexivity. Okay, so that's in essence, that's the picture I drew here. You're basically saying to show that something is a set, then every self loop, that this is the mini self loop, which I call the way I write reflexivity, up to higher homotopy. So that's the idea here. Okay, all right. So that's what we're going to do. Okay. So if we take this sort of path here, okay, and we look at the behavior of H. So if I take so H when instantiated. Okay. So let's write this out. So if we look at so we'll just notate H of X is of the form pi y in A. It's just clear if not X equals AY, then X equals AY. Okay, so that's what H of X is. So H of X, I'm fixing X. If you like, I could write X naught or something just to remind you. So if I fix X, okay, that's the X in question here. Okay, this X is there. So if I specialize my assumption about having stable equality to that particular X, I get a statement about arbitrary Y's. Okay, that's what I want to do here. Okay, so I have that guy. All right, so now if we look at the functoriality or the naturality of h of x in this position, because I have a path here, x equals x. So the naturality is going to say, well, if you give me any path in A, between y and y prime, okay, or excuse me, between x and x prime, then I'm going to get a certain thing. So what I'm going to do is I'm going to say this. If I do apd h of x, so the function in question is h of x, which has that type. All right, so I'm going to do that. And I'm going to instantiate this at P, which is a loop in A, all right, which is the domain here. All right, that's what I do. So I instantiate that. So then what I get is that I'll write it as P. You can write it with the path over, but I can also write it like that. It says h of x, this is the path over. Transport this into the other fiber, equals in some god-awful type here, which I'll leave open for a minute, is h of xx. Okay, so that's the idea here. All right, and the type here is what? Well, let's write it out just so we can be careful. It says not x equals ax arrow x equals ax. Okay, so we have that. Okay, all right. So that's what appd. This is the dependent. Remember, this is the dependent app. Okay, so the dependent app says if you have a dependent function that is a pi blah. Okay, it respects paths in its domain. So here's a path, and x is in its domain. Okay, x is a possible y. And the other thing, endpoint of that path, well, could very well be x. So we'll look at it as p. So now we're looking at the self loop, and we're saying, well, how does apd behave on that self loop? Well, there's the transport, which happens over here, and then we have an equation that looks like that. Okay. And so, as I mentioned, this could be written as a path over notation, which says that h of x is equal to h of x over the path p. That's the same, like that's just what we did by definition. Okay? All right, so now, okay, we have the following. So this guy is in a function space, okay? So we know that for any r, which is in, this is a function space, remember, because the negation is a function space. But we'll get to that. But right now, we're in a function. That arrow is what I'm considering. So by function extensionality, what we know is that this p lower star h of x applied to r is equal in x equals xa to h of x of r. Okay, so that's the first thing that we want to do. Okay, so that's just by function extensionality because we have a function, so we apply both sides to r. So you can see we're getting somewhere because we're getting toward something that seems to involve p is equal to something or other else within the right space, because we're trying to show an equation in that type, you see. So that's what I'm trying to get to. Sorry, so that's what I'm trying to do. So now there's a lemma that I didn't do at the board. So if you look at the book, there's lemma 2.96 gives us this. All right, and this is the following condition, which says that p star of h of x and r is in the appropriate type, which in this case is can be written like this: h of x p lower star r. Okay, so there's a technical lemma in here. Okay, so now, because this I'm going to claim is h of x of r, because negated propositions are props, the thing that I mentioned over there, because negated types, are props, homotopy props, meaning they have at most one proof. So those two things are equal, and where equal means that. And then if you calculate out what the action of transport is in an identity type, that's a post-composition. So this is h of x of r dot p. is what is written over here, and this is because of transport in identity types, which we talked about before. So that is given by post-composition, okay? And so now you can see what I do is I divide through by h of x of r, and so I get that P is equal to reflexivity. And we're working in x equals ax, so this has to be reflexivity of A, and that's enough, okay, for the result. That's what we needed. Okay, so yes.
So when you're using the negated types or products, you're talking about P star R and R, right?
Yeah, right, exactly. And so that way there's only one path. So these two things had to be equal, and then now I've got this times P, or concatenated to P, with P, whatever, times P. This times P is equal to this, so I just cancel the thises and I get P is equal to reflexivity. Okay, so that's a sort of argument for Hedberg's theorem. So as I say, it's a convenience because what it does is it tells us that it's a criterion, and it hopefully it makes sense. That once we boil it down and you look at the argument of the proof, it says, well, if you have a decidable equality. So for example, thing that comes out of it is, and this is quite trivial, for example, N is a set. I just asserted that earlier, but I didn't give the argument. You can prove this directly. You could just forget all this and just do a proof that N is a set. And if I remember correctly, that proof might actually be in the book. But it's easy with Hedberg's theorem because we know that for every x and y and n, either x is y or it's not. And so that decision procedure is enough to qualify it as a set. Okay? And how do you do this? Well, it's basically a double induction, right? You do an induction on x, just to remind you. So decidability means I have to write a function that goes from x and y and positively tells me what the answer is because it's constructive disjunction. And so what does it do is it does induction on x and induction on y, and if they're both 0, you can guess what's going to happen. So you do a double induction and you make a decision whether x is equal to y or not, and you positively determine that condition, and then therefore corollary n is a set, or natural numbers, nat. I think I called it nat before, sorry, but whatever, nat. Let's squeeze it in there. Yeah, I think I called it nat before. Okay, so nat nat is a set. Okay, so that's a very, very simple criterion. So lots of things like that. There's a number of things that you can just throw off easily because it seems it's easy to see in terms of that. Okay, so that's good. So that starts to make some sense, right? Because if you remember that there's this delicate issue about the constructivity of intentional type theory extended with univalence, let us say, which is the core of what is hot. As I've mentioned before, the computational meaning of that is not yet clear, but I'm going to talk as though it were, okay? And so the idea is that even in the presence of hot, what I wanted to say is the following thing. An element of this type means, as I just described it, I've got an algorithm that will compute from x and y and make a decision. That's the usual interpretation of law of the excluded middle in constructive setting. You have to remember that it means something very positive about running an algorithm, and moreover, that algorithm is extensional. I don't really use that very much here, but it respects paths in each of its arguments. But I have an algorithm that will do this decision, and but unfortunately, in hot, I can't at this moment, in all accuracy and honesty, make that statement because we don't have a computational interpretation which would really justify saying well, a proof of this fact amounts to a decision procedure. If I give you yeah, that's the problem, okay? And so I hope that that was a temporary state of affairs, but we've talked about that before, okay, that is the case. So I will, because it's baked into my mind that constructivity is to do with computation, I will probably often slip and you speak in terms of like decision procedures, but really, actually, it's not fair to say that. I have to be more formal and say, well, if this instance of excluded middle hold, then something or other is the case. Okay, just like to remind you. Okay, so but I have so many of my fundamental like thinking about constructivity is tied up with computation. I'm going to make that. Anybody have any idea where my eraser might be? You see one? Where? Oh, yeah, there. Thanks. Okay. Alrighty. Okay, so that's where I just wanted to finish that up. Now, a couple of other things I'll need to have with me. Okay. Which is going to be paradigmatic of what we will develop further, maybe next time, is the beginning of the idea of the fact that the levels, the homotopy levels of things, are cumulative. So the first thing is we can say that every H prop, well, sometimes I say H prop, every prop is a set. Okay, according to this terminology. Okay, so that's the next thing. So in general, what we're going to end up having is that every n type is an n plus 1 type, and this will turn out to be a minus 1 type, and that'll be a 0 type. So this will be a special case of the general thing. Okay. So what it says is, let's write this out. It says, well, if for every x, y, and a, x is equal to y, then for every x, y, and a, and every p, q, which is a proof that x equals y, that p is equal to q. Okay, so every prop is a set. Okay, so that is sort of set as what is being here. Okay, so we suppose we have a witness to this guy. So the witness is, let's call it f. So I have a function that will prove to me for any two elements that you give me will exhibit a path between them. Okay, that's the idea. All right. So this is you're going to see a similarity to the mode of reasoning I just used with Hedberg's theorem. So that's why I want to point this out. Okay, so I now want to turn that into a statement about paths between paths. Okay, so how are we going to do that? So it turns out a way to do this is we'll fix an x naught, and let g of y be, by definition here. Okay, I can define this be to the partial application of f of x naught and y. So where does that guy live? That lives in, you'll see the pattern, right? So we have pq in x naught equals y, p equals q. Forgive me for not writing the subscript there, even though I warned you that's a way to get into trouble. But okay, so but I didn't write that. Okay, so we have that thing. F of x naught and no, I'm sorry, I'm off by one. That isn't right. So if I specialize f, then I'm going to get, excuse me, I'm one step ahead of myself. Then I get that x naught is y is equal to a, right? Because that was what my f was. Okay, excuse me, sorry about that. I jumped ahead of line. Okay, so now, so we have a functoriality. So if we have a path, between y is y prime, because that's the thing I'm going to be doing, then we have a functorial action, right? So the functorial action is I take G and take its functorial action on P, all right? And what is it going to do? Well, we get a path over, or we can asymmetrize and do a transport. So this P lower star G of y is equal to in x naught equals a y, G of y prime, G of y prime. Okay, so I move this guy over to the fiber over y prime, which is here, and then I say that this guy is equal to that guy. So that's the setup here. And now we do the same kind of maneuver, right? So this works by post-composition. So that's G of y dot p, okay? And so we have that this is equal to G of y prime. And so we then just calculate. So we can say that P, another way of saying this is G of y inverse times G of y prime, right? I just divide by G of y. And so I'm saying that P is equal to G of y inverse times G of y prime. And if I take another Q, okay, if we do the same thing, is also in y equals y prime, then we discover by the same exact pattern of reasoning that Q is, lo and behold, G of y inverse times G of y prime, and so P is equal to Q. Okay, which is all I needed to finish that. So there's a kind of same style of move here, right? I have some assumption which is a pi. As it happens here, it was convenient to just fix one argument and look at an instance of that, which is G of y, which has this pi type. And you see, the idea is that AppD is the thing that lets me move up to this higher dimensionality equation. I have an equation here, and I need to say something about an equation between those identifications. And AppD is exactly the kind of guy that does that sort of thing, because it says this guy has to be functorial in G, so when I plug in a path here, it's going to amp up and say, well, modulo the path, the moving over to the other fiber, that the left-hand instance of this guy is equal at a higher type to the right-hand endpoint of this guy on that path, which is what we wrote here. The modulo is the transport. Okay, so modulo transporting the path, the G of the two endpoints are equal, or they're equal over P. That's another way of saying it. Okay, and then we just do that kind of calculation where we rely on what I gave you before, which was the action of transport in an identity type is given, it's a HOM, so it's given by post-composition the way HOMs are given. So it's the covariant HOM functor is what is being exploited here. Okay, so that's what's going on. Okay, good. So that's an example that says that every prop is a set. Okay, let me check my. Let me check where I am. I have a plan here. Okay, good. So that's the first thing. Okay. Now the next thing, which is related and is actually the same issue is discussed at length in the book in connection with equivalence, which is this fact that the statement that a type is a proposition is itself a proposition. Okay, so that's the first thing I want to say. And in fact, it's also true that the statement that something is a set is a proposition. Okay, so this is the next thing I want to look at. So the reason for this is, in a proof-relevant environment, you tend to shy away from making statements. Remember, we talked a long time ago about the idea of, we started out with the idea of A true, and then we evolved that to M is evidence that A is true. okay? Because in a proof-relevant environment, the proof is a mathematical object that is classified by the proposition or the type that it proves. And so we sort of shy away from making statements like A is true in favor of exhibiting the reason why A is true. And the reason for that is, and we've talked about this earlier as well, is that the reason why something is true is a datum that we can manipulate, and subsequent proofs might actually say something about the particular proof and its behavior. So for example, this will have definitional equivalences for certain m primes. M would be definitionally equivalent to m prime, and that can be relevant to even the well-formedness of some other a prime being a type, or in U, whatever you like to write, okay, that a prime is even a type. So we get this kind of dependency structure, the code-on-code dependency, which is from a modularity point of view is not a very nice thing about like hot libraries at the current setup. So we often find ourselves in that kind of situation. So it tends to be for that reason that we focus on saying something about the reason why. And sometimes at the board I've written out, I'll say, well, like I think I did this last time, I said, well, suppose we have some x which is in some relevant type A, and then I start doing reasoning and I say, well, I can't really be bothered to write down the program, but there's a program here which is in some other desired type B as a consequence of that. That's the typical thing I do. And I just say, well, maybe I ended up proving that this is equal to this in U, and then by transport I can transport this guy into here, and I didn't bother to write down that this would, in that scenario, would be transport in the identity to some path which relates A is equal to B. I just write underscore and just say, well, if there is a term here, in fact, a lot of times you don't even write that. You say, well, if there's a term here, then there's a term here. All right, so we do that a lot. Okay, that's life. I mean, again, I'm going to make that same mistake in a sense, but that's programming. I'm writing code, and all of my theorem proving consists of writing programs, and I write one program in terms of another program, and at certain points I'm interested merely in the fact that a program exists, and I don't care too much in a particular circumstance, I don't care too much about which program I wrote, okay? All right, so that can happen. So for informal work, there will be times where I'm lazy and I just write some underscores, and the idea is you or your proof assistant can help you fill in what that term is. Now, being lazy like that, as I've mentioned, can bite you because it often matters what you chose because of for example, this kind of a dependency. So we have to be sort of careful about that. We don't want to have code-on-code dependencies. But there are situations, and I'm going to amplify this general point more heavily momentarily, but there are situations where you can really say, it doesn't matter what I wrote here at all, because there's at most one. Okay? Now, it does matter definitionally, but we would like to get rid of definitional dependencies. So I'm ignoring that aspect of things, okay? But if there's at most one proof I could have written here, then it's perfectly legitimate in doing an informal argument to just say, if there's something in here, there's something in here, because I know is prop A and B, maybe, in the scenario that I have in mind, that may be the case, and then I am justified in being lazy insofar as I don't rely on definitional properties of the proof I wrote. So that's the issue that comes up. Okay, so I could in fact rely on its definitional properties, and I've discussed the fact that that's maybe not such a good thing. Okay, all right, but it is inherent in intentional type theory as it's currently formulated, and maybe one day we'll change that. But anyway, that's the way it is. Okay, so therefore it becomes relevant. That's why this comes up. It becomes relevant to know whether a particular type is in fact a prop. And in fact, the thing I'm going to do next, really, it becomes highly relevant to know whether whether a particular type is a prop. So the starting point that I'm making here is that we're justified in using the notation is a prop of A, maybe, one could say, precisely because this type, which could have been called any other random thing, this type has the characteristic that it is a prop, meaning that there's at most one way to prove that these things are equal. That these things, now see I'm jumping ahead, that this thing is a proposition. And the same thing for being a set. So I'll show you in a second how that works, okay? And then there's a whole chapter in the book pretty much devoted to, and I decided I'm not going to dwell on this, okay? So later, if you look in the book, I think it might be chapter 4 or something, but I don't remember, okay? There's a whole business in here about when is an equivalence between two types of prop. And the chapter in the book is concerned with what is the exact definition of this. Okay, because there turns out to be a variety of things you could choose as being the definition, the official definition of what it is to be an equivalence. And depending on what you do, it may or may not turn out to be a prop. So the one we worked with a lot was quasi-inverse, okay? And that's not. So let me not write it there because it implies. So the idea of a quasi-inverse, okay, that we gave before, which says you're given a mapping, so F is a quasi-inverse, or has a quasi-inverse, remember, was defined to be there exists a G, which is B and A, and let me not write them out, two paths saying that's left and right inverse, okay? So that was the definition of quasi-inverse. So that this thing had as elements triples G, alpha, and beta, okay? And it turns out that a given F can have many quasi-inverses. That is, there's not at most one thing that you could write down here that would express that F is a quasi-inverse, F has a quasi-inverse, that we can write that down. And so it ends up being that that's not the best definition for what is an equivalence, having a quasi-inverse, but instead there are other definitions that are given there. And the characteristic of them is the good ones, so to speak, have the characteristic that they are props. That is, there is at most one, up to higher homotopy, there's at most one proof that that A and B are equivalent, or there is an equivalence between A and B according to exactly what you mean by is an equivalence. Okay, so this is the thing that will come up later. So I'm probably not going to dwell on this very much. This is illustrative of what I wanted to do. First of all, was illustrate what is the issue. Okay, so let me figure out where I am now. My notes are all have gotten confused. Ah, yes, right. Okay, good. So let's do like the first one. Okay. So are you with me? It makes sense? So what we're just saying is this type is the sort of type for which it's pretty reasonable to speak of it being true without being too careful, okay, about the reason why. That's the idea of it, okay? So that's what we want to do. So how do we do? All right. So to be a prop, so I have to say, give me two proofs that A is a prop. Right? And what I want to do is I want to show that those two things are equal, well, wherever they should be equal, and is prop of A. Okay, that's the idea, right? So that's what it means to be is a prop. Okay, so it suffices to show, because if you look at all this, for x, y, and A, and now I'm going to do that thing. There exists some element, okay, of fxy equal, because this is function extensionality, gxy. Okay? Because remember what is prop is, it's no longer on the board, so I'll write it out for you. This says for every x in y and A, x equals a y, right? That was the definition of is prop. So So F and G have the characteristic that if you give me X and Y, which are in A, they give you a proof. Oh, this should have said A here, shouldn't it? All right. So this will say that they're written like that. That is not what I wrote in my notes, but okay. All right. Let's see. Okay, so now, okay. Right. Okay, good. So how do we proceed? So the argument I have written down here.
Wasn't it right wrong or
Yeah.
what you had before for the subscript?
Did I make a mistake? Yeah, sorry.
You were right the first time.
Yeah.
I was right the first time? Okay, right. And why was I right the first time? Because I realized that I depended on that. So this had better be right the first time, otherwise I'm screwed. Did I do this right? Because this,
If you just apply F to X and Y, then you get the type on the right.
right. Oh, okay, yeah. Okay. So this is good. All right. So we're good? Yes. Oh, yeah. Sorry about that. Yeah. I messed it up. Yeah. Okay. You see, it's easy to get confused. I chose not to spend time this semester on teaching you using proof assistance because that becomes a thing in itself. But eventually you start doing, using the machine for this, and then you don't make these stupid mistakes. Okay, so good. So now here's the point. So I have an element. So I have F and G is improp, is inhabited. Okay. So what we're going to use is, since is prop of A. So we know is prop of A because we have two inhabitants. So it's really true. I have two proofs of it. Okay. So since is prop of A implies it's a set, then the desired equation holds. Why? Because there's at most most one proof of an equation. So I have two proofs of that equation, x equals ay, and they have to be equal because being a prop, which I assume here twice, means for sure, let's write A, is set of A. And so if it's a set, it means that the equality, x equals y and A, there's at most up to that any two proofs of that fact, this one and this one, are equal. Okay, and we're done. Okay, so that's like a typical thing, okay? And you can do a similar argument. I won't repeat it here. You can do a similar argument, okay, to show that is set of A is also a prop. Okay, so that's all of the flavor of, when we start writing down, okay, when we start writing down types, and for reasons that are now going to be blatant, we start caring about which sorts of types are propositions in the sense that I've defined them to be. And sorry about the terminological snafu. Okay, so which of the types have the characteristic that they have at most one proof for the reasons I've sketched here. Okay, and now an even better, more like technically meaty reason for caring comes up. And as I mentioned, there's a whole chapter in the book devoted to what exactly should be the definition of an equivalence. And there are a variety of them, and there are many you could choose between. But the criterion that people care about is whether being an equivalence is a prop. Okay, so that's what ends up happening. Okay, so now what I want to do is talk about this idea of what is called the propositional truncation, which I brought up last time through double negation. So the propositional truncation, which is originally was called squashing, whether you like it or not. It was called squashing. Okay, so that's what we did. Okay, which is squashing. So you'll remember that the motivation, I'm out of chalk, you'll remember that the motivation that I gave, because it was historically accurate, is that assuming we're doing all of this for reasons of computation, there are other reasons, but one of the motivations I gave is that there are situations where I wish to suppress the computational content, okay, or squash the computational content of a type in order to really state, okay, in order to really state the kind of specifications of programs that we wanted to state. So we had some discussion last time about that, which I won't repeat here. And in the earliest form, we exploited double negation to achieve squashing. But what I was pointing out to you by bringing up the Gödel double negation translation, and I mentioned in Piazza that there are probably 10 different the Gödel double negation translations, but they're all, I gave you one, okay? And the thing that I wanted to mention about that particular one instance of the Gödel double negation translation is that it broke down into two parts, right? So the double negation translation, the double negation was serving two roles there. One was to suppress the computational content of the positive types, because the strictures of proof in constructive setting of disjunction, I was looking at the propositional case, so let's focus on that, of a disjunction, or for that matter, a void, are stronger than they are in the classical case, because a constructive disjunction has the meaning that you positively decide which summand you're in, okay, when you exhibit the proof. So since the classical logic is not up to that task, it doesn't achieve that. You have to suppress the computational content of the positives. So that was one aspect of it. And then I pointed out is, if all you wanted to do is truncate, then you could truncate an implication by truncating its antecedent and consequent, and that would be that. But it wouldn't be sufficient to capture classical logic. And in order to capture classical logic, I arranged that the double negation elimination come out true, okay, under the interpretation. So I said that the double negation translation of A implies B is A arrow the double negation of B. Well, their translations. So you might think that second, so what I said was, the translation of A arrow B, the definition that's in the Gödel double negation translation, you might worry about this, because after all, inductively, this is already squashed. This is already squashed. Okay, so what's left to squash? Why am I really squashing that squash thing? Okay, well, the reason is that it's playing a different role here. Here, the way I see it is, the reason for this being in here is to make it come true that not A implies A. Okay, because when you do it under translation, you'll end up with not A implies not A, and that's a dawdle, that's a triviality, and so it validates all of classical logic. So the double negation there has a role that is more than just the squashing in that translation, because here the role is really to say something about negation and not merely something about truncation. Okay, do you see the point? Okay, so that's why you squash the squash type there, because otherwise it's like puzzling, like, why did I need to do that? Okay, so I sort of bring that up. So that led us historically, and has led us here, is to consider a more abstract notion of truncation. Okay, so let's now look at an abstract notion of truncation, which I will present here at this moment as a primitive idea of hot, and later on we'll show how that could be derived from other things that we will introduce. Okay, so let's now look at abstract truncation. So what it does is it merely does the squashing and doesn't concern itself with trying to recover classical logic. That's a separate issue. Okay, that's the idea. All right, so that's the way to think about it. Except insofar as you feel that this use of the word prop has a flavor of classical logic lingering, but anyway, but it's to do with squishing down to there being at most one proof. That's the idea, so sub-singletons. So the idea about it is this, is that what you do is I introduce this type, surprisingly enough, it's called that, okay, which is I will just say, for this lecture, I will just say the truncation of A. Well, it's because this ends up being an instance of something even more general. In the general setting, you want to emphasize this is the propositional truncation, or what will eventually be called the -1 truncation. So this is the -1 truncation of A. So I'll just say truncation of A right now. okay? And that's what I'll do. Okay, so we'll find that. And it has an introductory form, which says, if you have M in A, then something is going to inhabit the truncation of A. So there needs to be some way of saying any inhabited type is inhabited, but it's going to be inhabited in a way that you're not going to care about, okay? So what it's done in the book is, and this led to some consternation recently, but it's not the way we did it in Perl, okay? But it's the way it's done in the book, so I'll stick with that. Is that there's some kind of an operator on M that, and then the consternation that arose recently on the mailing list is people find it a little unsettling that this thing appears to be a function of M somehow, that I'm not really saying that, but you're taking M and you're doing something to it, okay? So you put the vertical bars M in there. And so that's the way it's formulated, and it has some like slightly surprising. So this is the introduction rule, and to quell your nerves, the intuition here is that if you have M and N and A, then what I want to know is that what makes this squishing a squishing is that there's something, which I didn't bother to write down here, in the identity type of A, of truncation of A, which says that the squishing of M and the squishing of N are the same. Okay, that's the idea. So this is these could both be thought of as aspects of the introductory rule for the truncation. So that's written like that. So the idea is that whatever you're doing to M to achieve an element of this merely inhabited type, any two ways you did that are going to turn out to be same, at least up to higher homotopy. So the consternation on the web discussion had to do with the definitional behavior. Much of it had to do with, not entirely, but partly to do with the definitional behavior of this thing. Let's not talk about that right now, okay? But it definitely made a bunch of people feel uncomfortable. Okay, so what I want you to see here is that what I'm doing here is I'm essentially forming a quotient. So this is the quotient of A by the full relation. I don't know what notation to use for the full relation. You could loosely say A cross A, but anyway, the full relation, okay? In other words, because what I'm doing is if you read this logically, what I'm doing is I'm saying, you have some elements in here, one for each one in A. Oh, and by the way, they're all equal. Okay, by fiat, we stipulate there's something that goes there, right? A witness that says that these things are equal. So I'm really specifying a quotient. That's a way of thinking about it. We have to be careful about using the words quotient like that, because that, at least in like in ITT or in other settings, it's quotients by an equivalence relation, which normally one thinks of as a prop in the sense that I've been discussing, so one has to be careful, but let's just say loosely, it's some kind of quotienting by the full relation. So if I think of squash A as the quotient of A by the full relation, then it tells you what the elimination form has to be, okay? So the elimination form, the squash elimination form, what does it do? Well, in general for these elim forms, okay, I really ought to have all my gammas in there. Let me not do that, okay? So it says, if you give me an element of the squash of A, and you want to do something with that. Well, what's the obvious thing to do here? You say, well, pick an X in A and give me, let's get my notation, N in some B. All right, this is what I will write here. I'm going to say something more here in a minute. But then there should be an elim form that says I get a B out of it at the end. Okay, and I think I wrote in my notes, I wrote it as trunc m x dot n, but I don't know, call it whatever you like. Elim, squash elim, I don't know what the right word is to use there, okay? So the recursor, the eliminator for the squash type probably is going to look something like this, okay? Because after all, what went into the fact that M is in the squash of A? Well, certainly one thing that went into it is M. So in particular, you would expect the definitional equation by Gensen's inversion principle. If you gave me an actual M and A that you, so to say, squashed, then you would expect that that's the witness you plug in and you put it in here. Okay, so that's what you would think you would do. Okay, so that basically seems okay at a high level, except that I'm ignoring this part. In the discussion so far of how I got this, I'm ignoring this part. So you can obviously see, I gave you a hint, that if you think of it as the quotient, something is wrong, okay? Because I really ought to respect the implied equivalence relation, okay, in this, that n here, really ought to respect the required equivalence relation. The implied equivalence relation on A that is implied by the fact that I was working with squash A. And nowhere above the line do we see this, okay? So in New Pearl, we did this in the obvious way, which is we demand that you respect that if you give me any two elements here, we demand that the results be equal. Okay? And it worked like very generally for that reason. And we never had any problems. But and there's a good semantics for it in that setting. Okay, what we do here, and the way it's done in prop, is there's an additional requirement that goes on here, which says that this is all fine, provided you have evidence, okay, which really ought to be, parameterizing. Well, I need some proof. Let's call it P. So somewhere in here, I don't know where to put it, I need a P, okay, which is a witness of the fact that B is a proposition. You have to put it somewhere. And the reason is that now you can understand completely. So the requirement is prop of B ensures, it's sufficient anyway, ensures that, okay, n's behavior, let's put it that way, or n, is independent of the choice of M. Choice of the representative, I'll call it the representative, okay. The representative, I'll just write it like this, of the implied equivalence class. That's the way I like to think about it. Okay, the implied equivalence class. Okay, so there's an implied equivalence given here, and in the first cut at this rule, I failed to take account of it. So let's take account of it. And the way we take account of it is we demand, okay, that you elim into a proposition. Because propositions have the characteristic that any two elements of them are equal. So whatever I chose here, if it were M or M prime or M double prime or any of the other presumably infinitely many choices I could have made here, this guy won't care because it'll compute something definite based on the exact choice you made. But the results, though definitionally, let us say, may be different, propositionally they're all going to be the same because up to higher homotopy they're all the same. Yep.
But because they may be definitionally different, it seems hard to get that like beta rule where you have on the nose definitionally.
Yeah, so I don't remember whether that's the one that's in the book or not, but I believe it might be. the way I do these things, I just sit down and write them out in light of having been, yeah, so I'm not positive what's in the book, to be honest. So I should actually check that. Yeah, Favonia.
I have a question about does B depend on X?
Could P what, sorry?
B, capital B.
In the form that's in, I'm pretty sure the form that's in the book is this is non-dependent. I mean, it's given only non-dependently. Maybe later in the more general form, there might be a more general form. But what I'm doing is I'm trying to more or less go through the order of events in the book, and I'm pretty sure that this is the formulation that's given. So if Favonia was asking why maybe this shouldn't be like that. This should be something like, I don't know, X in truncation of A proves something P is prop of B. That's the suggestion here. And then this would be, you'd have to plug in for X, and I guess one would plug in M in B, and I'd have to think about whether that it feels like it should work because it's telling us pointwise that every instance I get out is going to be a prop. But let me not do that right now. Okay, but this might be a reasonable generalization. Okay, so let me not do that. Okay, all right. So yeah. Okay. So that's what I would like to say. There's something that, yeah, that's what I would like to say. Okay. So that's the notion of being an is-prop. And if you wrote out here, you might say that the right condition is here to say that essentially for every x, y in A, that, let me call it u and v just to stress, for the sake of stress, that u for x n be equal, in this case, let's just fix the b, v for x n. If b is a prop, this is certainly true. Okay, because that's what it means to be a prop. But in this form, you don't demand that b is a prop. So this is what we did in New Pearl. So you don't really care that b is a prop. What you care is that the guy that is splitting on it, the guy that is working on it, is independent of the representative. And this expresses that directly. So that's what I want to say. Okay? So this implies that, but I claim that this is the relevant thing. This is the thing you care, okay? Because otherwise it doesn't make much sense to have this here. Now, in Arbob's question is, I think that this equation is demanded definitionally, and it does show that there is a distinction that, and this was part of that discussion in the hot group, not entirely, but part of the discussion in the hot group, is that if you do, for example, this or something morally equivalent to it, you can observe things definitionally that you cannot observe propositionally, because propositionally, whether that was M or M prime, propositionally, they're the same, okay? So to speak, you can't see the difference, but definitionally you can. And then there was an additional twist having to do with a detail of how AGDA works that let you push that idea even further. But the idea is that definitional equality, that it does reveal something. So the question is, what constitutes a revelation of information? And the idea is, regardless of whether I phrase it as is prop or not, or phrase it this way, what I'm saying is they're equal up to higher homotopy. Okay, so that is going to have some effect on the computational. I mean, those don't necessarily, this and this are different relations, okay? And so that's, so this is a kind of weak requirement that says, as far as the internals of the theory is concerned, you can't tell the difference. But externally, one might say, judgmentally, you can tell the difference. So people have different reactions to that state of affairs. Okay, so now I want to say say something about the truncation. Oh, I'm out of time. Okay, I want to say something. That went by quickly. I want to say something about the truncation. Okay, so what I'll do next time is I will then pick up this idea of truncation. Okay, so let me take 2 minutes because there's something I forgot to say here, okay, which I'll throw in here. So we'll pick that up next time. So since I have a couple of minutes, let me throw in a couple of things. Let us define another proposition, another type related to the ones we've been doing so far, which is called contractibility. If you don't know it, this is called contractibility. Okay, so we say a type is contractible if it has an element and every other element is equal to it. So the picture I like is there's a guy there and everybody else has a path to it. So it's called the center of contraction. So it means that you can smush it. If you follow those paths, everybody will race to the center and collapse the whole type to a point. Okay? So, in fact, you can then prove a type is contractible if it's equivalent to 1. Okay? So you'll be able to do that. So let's define that as contractibility. Then it's actually a little lemma that you have to prove, which is that isprop, as I've defined it, is equivalent to, in fact, it might be, well, it's at least logically equivalent. I'm not going for my notes, so let me do this. Is logically equivalent to saying that the identity type, well, for every x and y, the identity type x and y is contractible. Oh, so I should write it like that. Is contour x equals ay. Well, what we said before was, yes, this is the idea, okay? So we can make this definition. Superficially, this seems stronger than the one I gave, but it's not, okay? So you can show that those are at least logically equivalent. I've forgotten what you do there. And the reason we care about that is, in order to use up my last few minutes, I'll throw this out, is because it leads to a very nice regularity, which gives us the numberings of the homotopy types. So you need that little thing. And then you say the following, make the following definitions. You say something is a -2 type if and only if it's contractible. So this is the thing I was telling you before, that in order to get notational conventions to line up, we start with -2. So a contractible type is also known as a -2 type. And then in general, you can say an n+1 type, and you need this lemma to make the whole thing work, okay, is defined to be that for every x, y, and a, the identity of x and y is an n-type. And that leads to the notion of is an n-type. So this is defined inductively, except that our base case is -2. Okay? And so if you work it out, you'll see is prop of A modulo this lemma is the same thing as is a -1 type of A, and is set of A is the same thing as is a 0 type of A. Okay? And then words begin to fail you, but at some point you can certainly get this far. Is a groupoid is the same thing as saying it's a 1 type. That's a 1 groupoid. And then the terminology that was pre-existing is there was a notion of a 2 groupoid. And that's the reason why we chose that numbering, because then we can say a 2 groupoid is a 2 type. And that feels nice. And then from there, I don't know of any specialized words from there. At that point, it becomes 3 groupoid and 4 groupoid. And so these become 3 types and 4 types and so on. So there are special case terminologies for the first 3 things. And to make everything work neatly, That's the convention. So modulo this lemma, which you have to actually prove, you have to actually check that this is really the case, okay? Then you can say nicely that there's an inductive definition. You start with contractibility, and then when you go up, you're just saying that something is an n+1 type if its identity is an n type. That's it. So that's kind of very smooth. It's very nice. And then you can prove in that setting, you can prove that if you have an n type in general, then you have an n+1 type. It itself is an n+1 type. All right, so this really should be for every a and u. If it's an n type, then it's an n+1 type. So it's a cumulative hierarchy. However, what you should not make the mistake of thinking is that every type is an n type for some n. That's not the case. Okay, because the being an n type is limitative. It says you go up to n and then everything else is killed off from there on. That's what's being said. Because if you unravel it, it just says the equalities of the equalities of the equalities, think of that as up or down, I don't know. Yeah, the equalities of the equalities of the equalities of the equalities eventually are contractible. So at that level, there's nothing to say. Okay? So there's types that have structure all the way to infinity. So you can't say that the types consist of the sum of all of these. That's not the case. But it's interesting, like here's an example, because when I say that this is the -1 truncation, the is-prop is really saying it's a -1 type. And then that will give us a notion of an n truncation. So this is the -1 truncation. Okay? That's what's going to happen. So I'll throw that in at the end because it's just like these are pretty minor observations that you can check for yourself or read about in the book, okay, that you can write all that down. So that's where the hierarchy of homotopy n types, how that is defined and where it comes from. Okay, thanks for your attention.